In this video, we're going to talk about the beta function, and it's a very useful function in mathematics that you'll learn in possibly college mathematics. It's used in differential equations, in multivariable calculus. It has a lot of different applications in solving integrals, and it's just really cool. We're going to derive a lot of really cool properties about the beta function on its own and derive a relationship between the beta function and the gamma function. Alright, so let's start with the definition of the beta function. Now, we use beta of xy as the beta function. And honestly, I don't know why they use the capitalized beta in Greek, because the capitalized beta in Greek is equal to the capitalized b in English, so you can't really see the difference, right? It would be better if we just use, beta of xy. But I like the capitalized b, so let's use it. This is defined to be the integral from 0 to 1 of t to the x minus 1 and 1 minus t to the y minus 1 dt. It's a very straightforward definition, and this is the first property. And we're not going to derive why this is the definition first, but defining this definition helps us derive the relationship between the beta function and the gamma function. But first of all, I want to derive a trigonometric form of the beta function. So first of all, let me write it. The trigonometric form of the beta function is this. 2 times the integral from 0 to pi over 2 of sine to the 2x minus 1 theta and cosine of 2y minus 1 theta d theta. So this is the second property we have to know, and let's prove why these are equal. And notice that here we have t's, right? We have t and we have 1 minus t. Now, notice that we substitute t as sine squared of theta. Then 1 minus t is 1 minus sine squared of theta, which is equal to cosine of squared theta. This means that there is a motivation for us to use this particular u substitution to derive our trigonometric form of the beta function. Yeah, so let's get started. Let's set u equal to sine squared of theta. This means that du is equal to 2 sine theta cosine theta d theta. And our limit is going to be changed, right? We're going to change our limit from 0 to 1 to, let's see, when t is equal to 0, we have sine squared of theta is equal to 0. So sine theta is equal to 0, which means that theta is equal to 0 because sine of 0 is equal to 0. And what about when t is equal to 1? Well, sine squared of theta is going to be equal to 1, which means that sine of theta is either negative 1 or simply 1. And it doesn't really matter which one you choose because sine is a periodic function. So however you choose the limits is going to result in the very, very same value. I'm going to choose pi over 2 because it's a convenient value, right? From 0 to pi over 2 is possibly the smallest difference you can get between those two numbers. Okay, so that's pretty auspicious, and now let's substitute it in. So initially, let's copy and paste our initial definition of the beta function. Initially, we had this. And now what we can do is we can apply our u substitution. From 0 to pi over 2, t is replaced with sine squared of theta. Oh my god. I should say t over here. Sorry. So it's supposed to be dt, not du. But you get what I mean. We're using a substitution. So t squared theta, x minus 1, 1 minus sine squared of theta, y minus 1, and our extra factor is going to be, let's see, well, dt is equal to this, right? So 2 sine theta cosine theta d theta. And now let's just simplify this. All you have to do is to simplify using simple algebra. And what you can see is you get our expression over here, which is really fantastic. Now, this is a very interesting form because it shows that the beta function is sort of symmetric, right? And it also gives us an opportunity to solve complicated trig integrals by plugging the numbers x and y into the beta function. And we'll be able to, solve for the beta function later when we derive the relationship between the beta function and the gamma function. Okay, so that's interesting. We now have two useful forms of the beta function, which really shows that it's pretty beautiful. Now, what we're going to prove next is, I think, one of the most important properties of the beta function. It's the relationship between the beta function with the gamma function. So beta of xy is actually equal to gamma of x times gamma of y over gamma of x plus y. This is really beautiful, and this is very, very important. Now, we're going to prove this property because now we know that gamma function is an extension of the factorial, right? So this means that if we have x and z, all we have here is a sort of, factorial expression over here, which is easy to derive. This is really beautiful because this gives us a better way to solve for beta. Okay, how are we going to prove this? The proof is as follows. So we're going to try to prove an alternate version of this. So we're going to multiply gamma of x plus y on both sides, and we're going to prove these are equal. We didn't really change much, we just rearranged the terms. So let's first consider the right hand side. The right hand side is gamma of x times gamma of y. Now, what is gamma of x times gamma of y? Well, by definition, gamma of x is the integral from 0 to infinity of u x minus 1 e to the minus u du times the integral from 0 to infinity of v y minus 1 e to the minus v dv. Now, because the variables in these integrals are separate, so they don't interfere with each other, what we can do is we can combine these two separate integrals, into an iterated integral. This gives us an iterated integral, and u x minus 1 e to the minus u v y minus 1 e to the minus v du dv. Okay, that's pretty easy. And now, how are we going to get this expression into this form? Now, we want to do a more complicated substitution, and I'm going to write it out first. U is equal to st and v is equal to s1 minus t. So why did we do that? Well, notice that beta has a 1 minus t and a t out front. So if we plug in v as s times 1 minus t, then this yields 1 minus t to the y minus 1, which is what happens in the beta function. And if we plug in our u as s times t, then what we have here is st x minus 1, and we have tx minus 1. And this is also present in the beta function. And the reason why we have an x factor in front is what we'll see later, is that we have a factor that cancels out the things in a very nice way. So why did I delete that? Yeah. We have the substitution. Now, also notice that u plus v, this is equal to s minus st, and u plus v is equal to st plus s minus st, which is equal to s. So s is equal to u plus t. And because t is equal to u over s from this expression, t is equal to u over u plus v if we substitute this in. We also have to calculate the factor. Now, in multivariable calculus, to calculate the factor that we have to multiply inside the integral, we have to calculate the absolute value of the determinant of the Jacobian matrix. And what is that? Oops. So the absolute value of the Jacobian matrix that is equal to the determinant of u s ut vs vt. And I'm using us to mean the partial derivative of u with respect to s. And these are pretty common, notation we use in multivariable calculus. So hopefully you know what I mean. This is equal to the absolute value of, let's see, what is this? So the determinant of u sub s. So u, calculating the partial derivative of u with respect to s, is equal to t. And doing the same for the other variables, what we get is s1 minus t and minus s. Let me just separate these. Yep. This is equal to the absolute value of minus st minus s times 1 minus t, which is equal to the absolute value of minus st minus s plus st. These cancel out, which gives us the absolute value of minus s, which is equal to the absolute value of s. And now s is always going to be positive, as we'll see later. And so this is actually equal to s alone. Fantastic. So this is a pretty nice factor that we have over here out front. Now we have to do the limit change. So how do we change the limit? Our limit was previously 0, infinity, and 0, infinity. And let me copy and paste our integral from up there. Now, we also have to resort to the expressions for each of the variables. Okay, fantastic. Now we have the information over here. So this is the limit for u and this is the limit for v. And when u and v is equal to 0, we have 0 for our s value. So this is the limit for s. And notice why, because u and v, they're always greater or equal to 0. And so if you add them together, they're always going to give 0 or a positive number. And because they extend to infinity, the maximum possible value for s is infinity. Now what about t? Well, t is the same for the lower bound, because u and v, they're all positive. And when u is equal to 0 and v is equal to some, 1 or other value, then our minimum value for t is equal to 0. And the upper value is 1. Why? Because if we consider this as a rational function, like x over x minus x plus y. Well, there's a horizontal asymptote if we take y to be some sort of fixed value, right? So if this is the case, then as x approaches infinity, or as u approaches infinity, what we have here is t is bounded at 1 because there's a horizontal asymptote. And therefore, the upper value for t is going to be equal to 1. Fantastic. Now let's get rid of this. And this is the value for t. And so we can use these limits now to derive our final expression. So we have to change the limits. This is from 0 to infinity, from 0 to 1. What's u? U is st to the x minus 1, e to the minus u, and u is equal to st. V is equal to s times 1 minus t. We have to raise that to y minus 1, and e to the negative s times 1 minus t. We have to multiply our Jacobian out front. And notice why s is always 0 or positive now, because from u and v, because s is equal to u plus v, and u and v are always going to be 0 or positive, s is going to be 0 or positive. Fantastic. These are really satisfying problems to do. And we have to multiply our Jacobian out front. dt, ds. And now we're going to do the opposite of what we did for the first integral. We're going to make this iterated integral into 2 separate integrals. And first of all, we're going to simplify this. how do we simplify this? Well, this is equal to s x plus y minus 1, t to the x minus 1, 1 minus t, y minus 1, and e to the minus s dt ds. I just did some algebraic manipulations over here. And this is because s and t are separate dummy variables, so they don't interdepend on each other. We can separate these two integrals. So we have the integral from 0 to infinity of s x plus y minus 1 e to the minus s ds. Now notice that we have ds over here because the limit 0 to infinity associates with the variable s. And so does the second one from 0 to 1 of t x minus 1, 1 minus t, y minus 1 dt. Fantastic. Now, it's easy to see that this expression is beta of xy. It's literally the definition of the beta function. Now, this integral is gamma when we substitute x plus y in there, right? This part is our z. So we have gamma of x plus y times beta of xy. This means that gamma of x times gamma of y is, oh my god, this is beautiful, is equal to gamma of x plus y and beta of x and y, hence deriving our special relationship between the beta function and the gamma function. Beautiful. And we have QED'd this particular proof. And just please remember this, because it just shows how a simple definition could lead to unexpected, sub-definitions and sub-relationships and sub-properties. To end this video, we're going to consider a property called the symmetry of the beta function. What's that saying basically is the beta of xy is equal to beta of yx. So you can swap the variables and the values of beta doesn't change. So that's pretty fun. Now, how do we prove this? Well, it's really easy. What we do is we can apply a substitution. Well, beta of xy, what is that? That is equal to the integral from 0 to 1. Oh my god, my integral sign is getting bad. Of t to the x minus 1 and 1 minus t to the y minus 1 dt. And if we apply the use substitution, t is equal to 1 minus s, then what we have here is 1 minus t is equal to 1 minus 1 minus s, which is equal to s. So t is going to be equal to 1 minus s, and 1 minus t is equal to s. So we have basically done nothing to the integral except swap the variables over. But it's still good to, rigorously prove this. Well, this means that our factor dt is equal to minus ds. Okay, now all we have to do is to substitute our variables in there. So we have 1 minus s, x minus 1. And we have 1 minus our t. But we have already shown that 1 minus t is equal to s. So all we have here is s to the y minus 1. And here we have a negative du. And what we also have to notice is that our limits change from 0 to 1 to 1 to 0. I didn't notice that when I was first writing it. But using the property from basic calculus, we know that this is equal to 0 to 1 as the negative one. So we now can cancel out the negatives, which yields the integral from 0 to 1 of 1 minus s, x minus 1, and s, y minus 1, du. Why am I writing du? It's always ds. Sorry about that. This means that this integral, which is equal to beta of yx, is equal to beta of xy. And hence, we have proved that the beta function is symmetric. Okay. Alright, thank you for listening to this video, and hopefully you found it helpful and not too confusing. But this is the power of mathematics, because it shows how you can derive different patterns from a very simple, dull-looking equation.